In the last video, we looked at how to do two-dimensional rotations in geometric algebra. In doing so, we found that certain multivectors represent rotations, and we called those multivectors rotors. But what exactly is a rotor, and how do we manipulate them? That is what we will answer in this video. This video is a part of From Zero to Geo, a series where we formulate geometric algebra, an incredibly powerful branch of mathematics, from the ground up. Before we get started with the video, I need to give a bit of an apology. I ended the last video with a promise that we would be looking at how to rotate by arbitrary angles, and I even used some intriguing notation to build your interest. However, upon getting started on that video, I realized that we need to spend a whole video on getting to know 2D rotors first. Thus, we will not talk about how to build rotors from arbitrary angles until the next video. And this does mean that my plan that I showed in the previous video is already incorrect. These things just take time to fully understand. Anyway, let's move on to the main topic of the video. What is a rotor? I introduced rotors in the previous video, but I didn't really define what they are. In general, rotors are the multivectors that rotate. This is the fundamental idea behind them. However, determining in full generality which multivectors are the multivectors that rotate is actually a very difficult question. But we don't need full generality here. Let's focus on just 2D rotors for now, where the answer is much simpler. From the previous video, we saw that the product of two unit vectors is a rotor, so let's use this as our starting definition of a 2D rotor. A 2D rotor is the product of two unit vectors. There are other ways to think of the product of two vectors. We have seen previously that the product of two vectors is a scalar plus a bivector. Thus, all 2D rotors are the sum of a scalar and a bivector. Because 2D bivectors only have one component, we can write all 2D rotors in the form a plus bi, where I is once again the unit bivector in 2D. But not all multivectors of the form a plus bi are rotors. Remember, rotors shouldn't scale vectors, so we don't want to count any multivectors of this form that do so. However, it is useful to describe all multivectors of the form a plus bi, even the ones that are not rotors. For historical reasons, arbitrary sums of scalars and bivectors in 2D are called complex numbers. So all 2D rotors are complex numbers, but not all complex numbers are 2D rotors. So which complex numbers are rotors? Well, it's all the complex numbers r such that multiplying r with a vector doesn't change the magnitude of that vector. We can even come up with a numeric way to check this. Consider an arbitrary complex number a plus bi. Multiplying it with e1 should produce a vector with a magnitude of 1. After working through the algebra, the final condition we get is a squared plus b squared equals 1, which just so happens to be the same equation as checking if a vector is normalized. We can use the same language here too. We will say that a complex number is normalized if a squared plus b squared equals 1. Then, 2D rotors can be equivalently defined as normalized complex numbers. Furthermore, we can define the magnitude of any complex number by using the same formula as for vectors. Currently, we don't really have any good way to draw rotors. They're the sum of a scalar and a bivector, and thinking of a mixed grade sum like this can be a bit difficult. However, in 2D, there is a useful alternative way to draw them. Instead of trying to draw the scalar and the bivector, we can draw the vector that is produced by multiplying e1 by the rotor. Given a rotor a plus bi, this ends up being exactly ae1 plus be2. So we can just think of the components of the rotor as being the components of a vector in space. The scalar part of the rotor corresponds to the x-axis, while the bivector part of the rotor corresponds to the y-axis. And we don't have to restrict ourselves to rotors when doing this. We can draw any complex number on the plane by thinking of its scalar part as an x-coordinate and its bivector part as a y-coordinate. We convert between vectors and complex numbers by multiplying by e1 on the left. And this actually works both to convert complex numbers to vectors and to convert vectors to complex numbers. When we want to draw a complex number, we multiply it by e1 on the left to get a vector. And if we want to get the original complex number back, we can just multiply on the left by e1 again, which gives us back the original complex number. So we can keep cycling back and forth between drawing vectors and complex numbers by multiplying on the left by e1. When we are drawing complex numbers like this, instead of saying that we are drawing on the xy plane, we will say that we are drawing on the complex plane. Now that we have an interesting way to draw complex numbers, what do the operations on them look like? Well, addition of complex numbers is algebraically identical to the addition of 2D vectors, so it looks the same geometrically as well. Same thing with subtraction. But multiplication is a little more interesting. When multiplying two rotors, we can multiply on the left by e1 squared. Then we can convert the first rotor into its corresponding vector, rotate it by the second rotor, and then use the remaining e1 to convert it back into a rotor. So we see that multiplying a rotor by a rotor in the complex plane looks the same as rotating a vector by a rotor in the xy plane. In the complex plane, the angle of a rotor's rotation is simply the angle between the rotor and the scalar axis. Thus, when multiplying two rotors, we can take the angle of the first rotor, add the angle of the second rotor, and the sum will be the angle of the result. In particular, multiplying a rotor by I rotates it by 90 degrees, just like with vectors. To multiply arbitrary complex numbers, we can do the same thing with the angles, and the magnitudes will just multiply. Unlike with vectors, the product of complex numbers is much more well behaved. For example, all products of complex numbers commute, while the product of vectors does not in general commute. Furthermore, it's actually possible to divide by any non-zero complex number. To find the inverse of a complex number z, we have to find the complex number z star that has the opposite angle of the complex number we are trying to find the inverse of. Upon multiplying, the angles will add to 0, and the result will only have a scalar part. Because z star is a scalar, we can divide by it to scale this down to 1. What do all of these operations look like algebraically? Again, for addition and subtraction, the equations are identical to the equations for vector addition and subtraction. For multiplication, it is a new equation, but it's pretty straightforward to derive. The equation for multiplicative inverses is a little more difficult, but not too bad. Given a general complex number a plus bi, the complex number with the opposite angle is a minus bi, and upon multiplying the two, we get a squared plus b squared. So if we divide by a squared plus b squared, the product will be 1, showing that a minus bi divided by a squared plus b squared is the inverse of a plus bi. Let's do an exercise. Please calculate all of these expressions involving complex numbers. They can all be reduced to the form a plus bi, so make sure that your answers are in that form. This is a computational exercise, so I will just show the answers in a few seconds. Before ending the video, I need to say a couple things. First, almost everything in this video only applies in 2 dimensions. Things get much more complicated in higher dimensions. You lose things like commutativity and invertibility quickly. It's honestly shocking how well behaved complex numbers are when the higher dimensional analogs are so different. The other thing I need to say is that even though we have been drawing complex numbers using vectors, they are not the same thing. The product of 2 vectors is not a vector, while the product of 2 complex numbers is a complex number. Furthermore, the product of complex numbers is commutative, while the product of vectors is not. Even though we are using the same geometric picture for both of them, they are incredibly different when it comes to how they work, both geometrically and algebraically. Anyway, now, hopefully, we will be looking at how to rotate vectors by arbitrary angles in the next video.